Hello everyone. Today I'll show the solutions to the Prairie Math League High School round 133 problems 5 and 6. To start, we have for problem 5, a polygon, a regular polygon with 1996 vertices. Here we're not going to draw the polygon because it's too difficult. We're just going to draw the circle that goes around the polygon. Now we need to delete a minimum number of vertices so that we do not have any rectangle inside this polygon. So first we note that if we have any rectangle in a circle like this, like below here in this diagram, then both of the diagonals must be diameters of the circle. And this is not so hard to prove because these four sides or lengths are equal. It's a property of a rectangle. And there's only one point that can satisfy this for this rectangle, and that is the center of the circle itself. So AC and BD both pass through the center, and so are both diameters. Furthermore, if we have any two diameters, then the 4 points must form a rectangle. And this is also not so hard to prove. We just apply this argument in reverse. Now, if two diameters both have an unremoved vertex on each side, so if we have in a circle two diameters, and all 4 points are points of the original regular polygon, and remember that we need to delete these points, but imagine that they're not deleted, okay? So 4 points that are not deleted. Then we have a rectangle, and rectangles are bad. So we don't want this. We want to have at least one diameter, in this case, that has a removed point. But, wait a minute. In the regular polygon with 1996 vertices, there are 1996 divided by 2 equals 998 diameters. So, yeah, I'm not going to draw these out. This is going to take an eternity. But you get the idea. Now, if we have at least 2 diameters, such that these points are not removed, then by this argument, something is going wrong because we can't have rectangles. So, what does this mean? At least 2 doesn't work, so we can only have at most 1 diameter with both removed points. And any other diameter of the circle has a removed point. Okay, these are not diameters, but you get the point. So we must have 1 diameter with both vertices. So for the remaining 997 diameters, we must have 1 removed vertex, or else we're going to run into this same problem. So we have to remove 997 vertices. Therefore, the answer is C. For problem 6, we have this expression where A1, A2, it's A3, etc. to AN are the numbers 1 to 3 until N in any order. And we want to find out the parity of S. Now, we're going to use a bit of a trick here. Notice that if we have any number, let's say 3, now let's square it, so we get 9. 3 and 9 are both odd. If we try an even number such as 2, and score that, 2 and 4 are both odd. Both even. So notice, for any number, x, if we square that, we're going to get the same odd or even, or the same parity. Hence, for each one of these expressions, we can drop the square. It will change the number, but we don't care about the number. We care about the parity. So, in this case, we drop the 2. A sub 1 minus 1. Yes. Now, repeat. Drop the 2, etc. And we repeat this for everything. And now we get a new number t. Now, as we see, t is pretty much never equal to s. except in like exceptional circumstances. But we don't care about that. We only care about the parity of S. Now T, remember these are just numbers 1, 2, 3 to n in any order. So A1 is going to cancel out with, like, if A1 is 3, then it cancels out with 3. And as we see, these all cancel out because the numbers 1 to 3 n in any order, and these are the numbers 1 to 3 to n in a specific order. But regardless, they cancel out, and T is 0. Now, T is 0, and 0 is even. So, S is even. And the answer is B. Thank you for watching.